The method of classification of stars.
Now that we are about 1 billion years into the history of the universe, we can see a panorama of stars swirling around in galaxies, which have in turn collected into clusters and superclusters. So what happened next? The answer to this question will require that we learn more about stars and their characteristics, which determine the way we categorize them. So let's learn the basics about this system now. When we first started to observe stars in telescopes, we divided them into color classes: white, yellow, red, and deep red. This was later refined, and each color was broken up into letters: A to D for white, E to L for yellow, M and N for red. Later, it was realized that things made more sense if stars were categorized by surface temperature. But this letter system was retained because all the work to classify stars had already been done. So from hottest at around 25,000 Kelvin to coolest at around 3,500 Kelvin, we now have O, B, A, F, G, K, and M stars, a classification system called the Harvard system, which was developed by early astronomer Annie Jump Cannon. This sequence of letters is rather unintuitive, but to remember the order, we can use the following mnemonic. Oh, be a fine girl, kiss me. Feel free to replace girl with guy, depending on your persuasion. Or if you find the whole thing terribly sexist, just make up your own, such as, omniscient beings are firing gigantic knowledge missiles. As we can't stick a thermometer into a star to see how hot it is, this classification, based on temperature, is actually derived from Wien's law regarding black body radiation, which we saw in the Modern Physics series, as well as other types of data, like emission spectra. We analyze the light we receive from a star and correlate it with a particular temperature, as well as with specific elements, just like when we learned about the Bohr model in general chemistry. The hotter the star, the more of the hydrogen and helium nuclei that have been stripped of their electrons, forming the phase of matter known as plasma. The hottest stars, O stars, show very little hydrogen because most of the hydrogen is without an electron and thus can't absorb and emit light. Helium is still able to retain one or both electrons, and thus we do see emission correlating with helium. Cooling down a little with A stars, suddenly hydrogen can hold on to an electron, so the spectrum changes. Getting cooler still, some bands show up that correspond with metals, like calcium. So the convention is derived from temperature, but this happens to correlate with color and size as well. Hotter objects, like O and B stars, are blue, and cooler objects, like K and M stars, are red. Also, hotter stars tend to be larger and burn brighter, with the additional heat resulting from the fact that so much more fuel is being burned. All of this data regarding temperature and luminosity, as well as indirect information on mass and radius, can be represented on something called a Hertzsprung-Russell diagram, or an HR diagram for short. In this diagram, the horizontal axis shows temperature decreasing to the right, and the vertical axis shows luminosity, or the amount of energy emitted by a particular star per unit time, increasing going up. We can see that the majority of stars fall on a continuous curve, which we call main sequence stars. 90% of all stars follow this trend, including our own sun, which is part of this yellow region here. Some stars, like red giants, are very cool yet luminous, while others, like white dwarfs, are very hot yet dim, but the majority belong to this main sequence. Even though this diagram lists only temperature and luminosity, we can infer many things about other variables.
I'm going to stop it there. We don't need to get into the mathematics, just the general concepts of heat in stars, how it's generated, and what happens to the spectrum as the stars cool or reduce in temperature. That's it.